Welcome to the lecture on finding equation from this graph. This is kind of a summary of what we have done so far. So on vertical shift, amplitude, period, and phase shift. This time in this section, we're going to look at from the other side that we have a graph given and we're supposed to come up with the equation. And this is how it's going to work. So here we have a graph given. And I'm not exactly sure if you can read those numbers in eLive. I kind of doubt it, but I hope that they came through on your hard copy. So we're going to look at the graph. We're going to determine sine or cosine. Usually that it could be either one of them. I'll make a note of that, or I mention that later again. But usually the way it's determined is where does it start? And it seems to start kind of it's on a zero line here, so we should come up with a sine. Then we're going to look at, for example, doesn't have to be in that order that we look at amplitude next, and then period and so on, but we could look at it in a different order as well. I'm going to look at period next, so it goes 3 up, and it's going 3 down, so we have an amplitude of 3, and it's correct right side up, so it's a positive 3 in the front, and then the whole period here, it starts at 0, then goes to pi over 2, pi, 3 pi over 2, 2 pi, so we have a total period of 2 pi. Okay. And as we can see, we have no phase shift, so phase shift equals 0. And of course, I might have mentioned earlier that we have no vertical shift, so vertical shift equals 0. Okay, now from the P here, from period, we're determining what the coefficient B is by plugging it into B equals 2 pi over period. So 2 pi over 2 pi is 1. So we have a simple x within the sign, 1x of course. And the C is being determined by the phase shift. So C equals negative B times phase shift. So negative 1 times 0. So we have no phase shift and no coefficient 0. Okay, so that's it. Y equals 3 sine x is the equation for the for this graph. Okay, the next one. As you can see on the next one, I graphed apparently 2 periods. It again goes all the way up to 2 pi. That means that it has to be faster, so we should come up with a value that is with a value for b that is larger than 1. 2 periods here fit into 2 pi. That means 1 period fits into pi, so I'm going to use that. It looks like we have an amplitude of 3. It sure looks like it. We have no vertical shift. It looks like we have a sine curve, and it sure looks like we have no phase shift. With no phase shift, the coefficient C is 0 as well, because we're just multiplying coefficient B, whatever that is, by 0. The coefficient B is period. B equals 2 pi divided by period, so it's 2 pi divided by pi, which means we come up with 2. So we have 3 sine 2x as the equation for our graph. Okay, I'm gonna copy this down here so we'll have it available for the next few examples. Okay, this next one here apparently starts higher. This is one way of doing it. We kind of estimate where the 0 line is, and it looks like it's 2 up. So vertical shift must be plus 2. From that 0 line here, plus 2, we can go 3 up and 3 down, so we have an amplitude of 3. Alternatively, what I also do is I look at what is the total here from the crest to the trough, and I see it's 6. And then I divide by 2, I come up with the amplitude is 3. And then from there I can say, okay, I start at -1 here for the trough, and then I go 3 up, and that my zero line therefore must be at 2. Either one of those two ways. Again, it seems like we're starting at 0 here, at the 0 line for the sine, so we come up with a sine curve. We have no phase shift apparently. And again, it looks like we have, it stretches over 2 pi for 2 periods, so period is simply pi. With period pi, the coefficient b equals 2 pi divided by pi, which is 2. And c, with phase shift of 0, c as well comes out to 0. So we have an equation that says 2 plus 3 sine of 2x, equation for this graph. And you can easily check that on a graphing calculator. I'm going to save that this time around, so we're not going to go to the graphing calculator. Okay, and I believe I have one more. Okay, this one again starts at a 0. So here it's going to be a sine. It looks like it has an amplitude of 5. It looks like it's actually upside down, so we should come up with a -5 in front of the sine. Looks like we have no vertical shift, so that's 0. The period, well, again, you might not be able to read these numbers in eLive. I hope in the script you are. This here is -0.5. This is 0.5, 1.5, 2.5. So it goes from -0.5 to 1.5 is 1 period, so p equals 2. There is a phase shift. Notice it starts at -0.5. So I have -0.5. B equals, well, that's going to be 2 pi divided by the period, so 2 pi divided by 2. So we have period b, coefficient b equals pi. Okay, the coefficient c this time around is going to be -b times the phase shift, so -pi times -0.5, so we have positive pi over 2 for positive pi over 2 for the coefficient c. And let's see if I have pi here. There it is. Okay, I'm going to take a breather here and double check that. Let's see, -pi times -pi. Yep, okay. So we have -5 sine pi x, and then plus pi over 2. Okay. What I want to point out at this point here is that we could have come up with a different equation. What's this one? We could have come up with -5 cosine pi x. How? Well, it starts here with a negative cosine, and then goes all the way up, and then ends with a period of 2, so we have coefficient of pi. That particular cosine is upside down, that's the negative, has an amplitude of 5, and it has a period of 2, therefore for a coefficient of pi, and there is no phase shift. Which of these two is correct? Both of them are indeed correct. Why are both correct? Because sine and cosine are very much related. So we have some ambiguity in here. Ambiguity, sorry. But which one would we prefer? Well, as I said, both of them would be correct, but we would prefer the one where in the graph it starts out. So right here, that's where the graph starts out, and that kind of tells us, well, that's going to be a sine curve. And we'll see that in the problem section, we have certain problems where that's better emphasized. Wherever it starts out, that's the preferred one. However, keep in mind, the other one is actually just as correct. With that one, I'm finishing up this lecture on finding an equation from its graph. Okay, let's go ahead with our lecture on combinations of functions and graphing them. So here we have cosine x plus cosine 2x, and I'm just going to go to the graphing calculator and see what's happening with that one. Okay. So cosine x, as I had already mentioned, it would be really tough for me at this point to actually try this in Paint and figure out how it looks like. So we'll just look at it here. Let's look at the window. Let's start with 2 pi at first. Scale isn't really that important. We're adding the two cosines, so each of which has an amplitude at 1, so possibly they could go all the way up to 2 or negative 2. So let's see what we get. Okay, and it actually kind of looks like a polynomial of 4th degree, where we have a relative maximum and 2 relative minima. Let's actually see how it looks when we extend the window. So let's do this here, 8 pi again, I guess. And it keeps doing this. So it changes kind of between small amplitude and large amplitude. Okay, let's go back to the lecture. So the function value changes between small and large amplitudes. Let's see what happens when the periods of the two individual trig functions are relatively close to each other. So this one here looks almost the same as the one above, except that as we have here 2x just as well, we have 1.9x instead of 1x as above. And then it says here I should change the window from negative 100 to 100 for x, so I guess we'll see what happens then. So same kind of, virtually the same kind of function. So I'm just going to get in here and insert a 1.9 as a coefficient. Of course, we're looking at coefficients of 1.9 and 2, which means we're looking at periods of pi and tiny bit larger than pi. Okay, let's see when we graph. Okay, we can see a little bit over the span of 8 pi. Something is happening, it's decreasing. And then I made myself a note there where it said graph it from negative 100 to positive 100. And I don't know really if the scale matters. And let's see what we get. So this is pretty much what it's doing here. It goes from very large amplitudes to tiny amplitudes. If this was played as a musical note, let me copy this one here. If this was played as a musical note, then what we would hear is a large amplitude, so it would be loud, and then a small amplitude, so it would be quiet, and then loud, and then quiet, and so on. And pretty much what we have there is what is called a beat that we're trying to match up a frequency, for example, of a tuning fork with the frequency or pitch of a tone of an instrument, and that's how an instrument is tuned. What the musician doesn't want is that particular beat. The amplitude shouldn't go up and down, listen to that beat. So what the musician is actually looking for is, when does that beat disappear? When will that 1.9 here match to 2? So what the musician would be doing is he would be trying, or she would be trying to change that coefficient V, or the period of the frequency that is being played, and therefore match the tuning fork and therefore have the instrument tuned. And that's pretty much what I say here. Okay, let's look at one more thing. Whoops. Accidentally push myself completely somewhere else. Another application of combining trigonometric functions is by Fourier series, and they represent certain waveforms, and they can be used in physics and engineering and electronics to look at wave functions of electronics, for example. So here's one, and notice it looks really complicated. Pi over 2, that's just a vertical shift, right? Minus 4 over pi, that's just an amplitude with upside down, I guess. And then it says cosine kx over k squared, with the k being odd numbers, 1, 3, 5, and so on. So what we have in here is cosine of x divided by 1. Then we have cosine of 3x divided by 9. Then we have cosine 5x divided by 25. And everything is added here. Of course, this is sigma for adding. So we have all these functions added. So we come up with something similar to either one of these, but quite a bit more complicated and some kind of certain shape. So we're going to go to the graphing calculator and see how that is going to look like there. And this is what we would have to type into the calculator, where of course you recognize the pi over 2 minus 4 over pi times. The sum sequence here is what substitutes for the summation sign, and then it goes in here cosine kx divided by k squared. And then the k is supposed to run from, well, 1 to what number. This here indicates infinity, but it would take the calculator forever by definition. So I decided to go from 1 to 15 in steps of 2. That ensures that we go 1, 3, 5, 7. So we just cover the odd numbers. Okay, let's do that on the graphing calculator. Okay. Let's see, where's my graphing calculator? At this point, let's see what happened here. I almost wanted to give up because my computer almost stalled. I hope this is going to work. Well, let me give it a try. I hope it's recording here. All right. So it said pi over 2 minus 4 over pi times. And now the sum sequence, you have to know a little bit more about the calculator. One sure way to find it is in the catalog, where everything is alphabetical. And then I'm going to hit my green S here, and then I go all the way down to, bummer, I think I'm going to hit my green T and go one up. So green T. And now it's not doing it. There we go. All right, there we go. There's the sum. That's what I wanted. And then the sequence I can also get from there. So second catalog. You also find that elsewhere. I believe you find it under stat or math or something like that. But this one here is in the catalog. You find everything that the calculator has. And there's the sequence that I wanted. And now it opens parentheses for the cosine. So cosine of k, that's alpha k, where did it go? There, times x. Parentheses, divide that cosine by alpha k squared, comma, alpha k, comma 1, comma 15, comma 2, parentheses. That's the, let's see how many parentheses I have to close. Oh, quite a few actually. No, I think just one more. The first one was for the sequence, the second one for the summation. Okay, go to window. And no, I don't want to graph between -100 and 100. So 0 to, let's make it 4 pi. Scale, I don't know if that really matters. And then y min, y max. Looks like we have an amplitude of 4 pi, which is roughly 1, and we have a vertical shift of pi over 2, which is 1.5. So maybe I want to be between -3 and 3. That should work okay. Actually, maybe -1 will work. Okay, let's see what we get on a graph. It graphs really, really slow because it has to calculate a lot. I mean, after all, we put in all these odd k's. Oops, it's shooting up a little bit too high. Well, because it has to calculate 8 different cosines running from 135 all the way through 15. That kind of looks like a triangle. Yeah, in fact it is. It's a triangle wave, so to say. And people who work in electronics encounter those and would be interested in these Fourier series. Okay, I just let a graph here. And then we're done with this lecture. Okay. Let's see if I can actually go over to where it started acting kind of funny earlier. And it works kind of funny for me right now, so I'm just going to stop right here.